So great. So let's get started. So welcome back, everyone. Uh, so let's see. So today, we're going to be talking about the singular value decomposition and PCA. So how many, just to kind of check, how many people have heard of the SVD before? How many people have worked with it? Okay, but how many people have not really worked with or heard of SVD before? Okay. Yeah, okay, so this is about what I expect. I think probably most of our undergrads are now trained well by the time they get to this class, but not all of the graduate level students. This is yeah, so how many people did the singular value composition in a linear algebra course as opposed to in the, and how many, okay, and how many did not, had took a linear algebra course but was not covered? Okay, yeah. How many people took a linear algebra course and eigendecomposition was not covered? Not, okay. Okay, so, well, most of you have seen, okay. The linear algebra course here is not always covered eigendecomposition even, which is so okay, so we're going to go talk about singular value decomposition today and relatives getting up to PCA, connecting hopefully to eigendecompositions. Many of you have seen some of this before. Hopefully it's maybe not my presentation of it before. And I'm hoping it's something that I think is useful to see multiple times. So hopefully that's okay still. For those of you who haven't seen it before, it'll go probably a little bit fast because we're going to cover what I would prefer to cover over 3 or 4 lectures, maybe in 1 lecture today. Okay, yeah. So, okay. So, again, we already pre-processed this by talking about when we have data, and now we'll call our data A, A1, A2, up to AN, and each of these is going to be an element of RD. Sometimes I'll say now A will be an element of Rn times D. The difference here, just a notation, this is a subset, so this is n points, each in a d-dimensional space, so each of these is a d-dimensional vector, there are n of them. It's saying the whole matrix is an n by d. In some sense, it's equivalent to being in an n times, so if n is 100 and d is 20 in a 2000 dimensional space, but you write n times d to kind of let you know it's a matrix. Okay, so A is a matrix. And we're in the situation where we want the dimensionality to be, we think there's a lot of data and then we want the dimensionality to be lower. Again, we can think of A now as this rectangle, and any row in AI, is one of these kind of these data points, which is a row vector in RD, right? So this means that there are D columns, and there are going to be n of these rows. Yep. Well, okay. And we're going to apply, so dimensionality reduction. Okay. We are going to want to be in one of two settings with like the data matrix. One setting is that each column has the same units, and these are comparable. It makes sense to kind of add 2 columns together. That would be something, or take an average of 2 columns. That would kind of make sense. Okay, so averaging among columns would be something that would make sense to do from the point of view of units, what they contain. The other is that it's a learned kind of representation. So this might say it's distributed. So this is in the sense where each column does not actually mean anything specific. That will be the outcome of what we talked about today as well. Each column will not mean something specific, but the meaning is distributed across the columns. And this is a much more common way of having your data represented now. It's often after some sort of embedding approach, where you've either used done contrastive embedding or a mass modeling or some neural architecture, take the last layer of it, something like that. Right. So we want to think of these sort of questions, and can we come up with a then the goal is a mapping from RD to RK. And I talk about this kind of in two somewhat confusingly interchangeable ways. One is where the result of applying this is actually going to still be in RD, but on a k-dimensional subspace. Okay, and the other option, or mu, and maybe we'll call this mu bar of A, is going to lie in RK, right? So it's only going to have k coordinates, right? So this output, there are kind of two ways of thinking about it. The output will either still be a point in the d-dimensional space, so the representation will still have d coordinates, but I'll know it lies in a k-dimensional subspace, or it will actually, I'll give it only k coordinates. So it'll be in that subspace and I'll have coordinates defined in that space. So it's a different coordinate system. Okay, and hopefully the distinction, we talked a little bit about this on Monday, and we'll see a different way of thinking about this today with the singular value decomposition. If you kind of ignore one part of it, then you get the bottom part where you get the projected to the low dimensional space. If you reconstruct everything in the low ranked version of the SVD, then you get something back in the d-dimensional space. Okay, so keep these. This can be kind of confusing, so let me kind of these two options are commonly used. Okay, and we want to talk about a projection. So, and in fact, we want this to be linear. Okay, a linear projection. Again, we call this a mu. I call this a mu function, or actually, let me call it, or mu, which is going to be equal to a pi function for a projection onto a subspace F of a data point X, right? So we want to, what does this projection do? We're going to define F using a set of basis functions, u1, u2, up to uk. Okay, each uj is going to be in RD, a d-dimensional vector. Each uj is going to have that it's going to be a norm one, so it's a unit vector, and I'm going to have that uj dot uj prime is equal to 0. This is going to imply that uj prime are orthogonal to each other. Okay, and so this is going to be useful because I'm going to have these vectors u1 and say u2, and when I have a data point X, there's somehow this, you can think of this subspace here, and I'm going to project X down onto the space, I of f of X, and this is going to have two orthogonal components. Okay, this point here is or this length here is going to be u1 dot x, the dot product with x with u1. This length here is the dot product of u2 with x. Okay, but this actual vector here is going to be u1 times the dot product u1 with x, where this component is the length right? This is the length of it, and this tells me what direction to go that distance. Okay, and because U1 and U2 are orthogonal, I take these two components and I add them up. Right, so then pi of f is going to be equal to U1 U1 dot x plus U2 dot x. I can think of this as the projection onto U1 of x plus the projection onto U2 of x. Okay, because they're both vectors, d-dimensional vectors, I can add them. Okay. Or I could think of this point, I could also think of this as I of f of x bar. This is going to be equal, then pi of bar of f of x is going to be a two-dimensional point. That can just be the coordinates, u1 dot x. That's the first coordinate, u2 dot x. That's the second coordinate of the vector. This is now a vector in 2 dimensions, right? Where this tells me the first coordinate, this is the second coordinate. Okay, and these are different from the original coordinates system I worked with. Okay, these are projections. We talked about this again last week, on Monday this week. And then quickly we talked about, just to summarize, random projections. Okay, and this is often where you want D, think of like 1 million, and K equals, say, 500. And so I want to project in this sort of setting. This is where this works. And so I basically pick each uj at random, and these are independent. So I may not, I'll have uj dot uj prime is going to be approximately 0, but also not equal to 0. So that means if I pick two random vectors in very high dimensional space, they're going to be almost orthogonal on average, but not exactly orthogonal. And this basically still works. Okay, so the early approaches towards these random projection things, they picked a bunch of vectors at random, and then they orthogonalized them, and then they did the projection. And it turns out maybe it helps a little bit, but it's usually not worth the effort. Okay. The interesting thing about this, I think, one is that this can preserve all distances, okay, up to 1 plus or minus epsilon. So I have that x, let's say x minus x prime, 1 minus epsilon is less than or equal to, say, the projection of x minus the projection of x prime, 1 plus epsilon x minus x prime. Okay, so this is my k-dimensional space, right? And the distance is approximately preserved. And to get this to work, I need k equals roughly 1 over epsilon squared log n. It's probabilistic, so there's some probability of failure. Okay, so interestingly, it scales quadratically with the amount of air that you want. This is from similar things we saw with hash functions for the min hashing. Have a similar sort of analysis here of why you need 1 over epsilon squared here. So if I want 1% air, I need a factor of 10,000 in front here. If I want 10% air, then I need a factor of 100 roughly. And it's logarithmically on the number of points. This holds for all points and all pairs of points, and it grows logarithmically with the number of properties I need to preserve. This means if I want, one way of thinking about this is that if I have n orthogonal directions and I want to preserve all of them approximately, so they're all approximately orthogonal, I can preserve them in logarithmic number of, I can project them down into a logarithmic number of spaces. So if I had d dimensions and I had all these orthogonal components, I wanted to preserve all the properties of them roughly up to some epsilon factor, I could fit them in log d dimensions with some distortion. So the factor tells me how much distortion, and how much I scale the log d dimensions tells me how accurately I represent those in that space. Okay, so it's not quite log d, but maybe 100 times log d. So you can really pack a lot more things into a lower dimensional space if you're willing to give up exact orthogonality. So some things are kind of accidentally correlated with each other. Okay, so this is the cool takeaway here. And in this regime with a really high dimensions, going down to kind of a still high, but not too high dimensions, this is kind of the right way to approach it. But if I want to go down to a much lower dimensional space, then this is not going to work so well. I'm not going to preserve most of the information I want. Okay. So why would you want to go down to a lower dimensional space than 500? 500 seem good? Yeah?
Maybe you want to put it on the 2D.
Yeah, great. You want to draw a picture, right? So this is a really big motivation for this. And so from actually a bunch of psychiatrists effectively had a bunch of data they were collecting about kind of patients, and they wanted to project into a two-dimensional space. In the 1950s or something, they published ideas on doing this. They wanted to be able to draw pictures of these things while preserving information. I won't be able to preserve this all distances property anymore. I'm going to have to give up on this property. Okay, to have this property where all distances are approximately preserved, I really need this high dimensional space. But for things like machine learning applications where I create these embeddings, there are 500 or 1,000 dimensions because of these reasons. Because otherwise I can't really preserve all the information, all the distances I want for these really big data sets. Okay. Okay, so instead, we're going to look at a different objective, the sum of squared errors. Okay. Call this SSE objective from A down to B, and I'll stay with that thinking about here. Okay, so the sum of squared objective from A to B. I'm going to write this now as a sum over all the data points in A. From that data point to its projection onto the subspace defined by B. And I'm going to square it, right? So summing. So for every data point, I'm going to look at how far is it projected onto a subspace. And I want this to be, and I'm going to take that distance, I'm going to square it, then I'm going to add these things up. Okay, why do I use squared distances instead of just distances? Why don't I just preserve sum of distances? A distance is always positive. So if I take this has it's Euclidean distance, so it has to be positive already. It's mostly because it's easier to work with. Okay, there's some advantages to doing kind of stuff with the sum of the distances that might be a little bit more robust to noise. And so some people have figured out how to do that, but it's way more complicated than this. I can use a bunch of nice linear algebra tricks. The Pythagorean theorem is going to show up here, and the squared distance will be a lot easier to work with. Yeah. Correct. Yeah. So the projected space, remember, this will be the projection that still lives in RD, still lives in the d-dimensional space, right? And this is defined by a subspace D, right? So I'm in this high dimensional space here. I can think of each of A as a point in the space, and I've got a set of these points, and I'm going to define a subspace through here, B, that's going to be k-dimensional for some k much less than d. And then I'm going to be projecting each of these points onto the space. These are the residuals of this projection. And each of those purple lines, I'm going to take that distance and I'm going to square it, and I'm going to add those up. That's my area. And so the projection, if this is a point AI, this right here is going to be projection onto the subspace B of A. So it's still an RD. Yeah. And this, yeah, it depends on, maybe you're looking right at the cross section of the plane, maybe it's one-dimensional, right? It's hard to draw these things. Yeah, I can, but you can think of it as, I think, thinking of it as one or two-dimensional in this picture, both of those kind of work. Right, yeah, I mean, going from 3D down to 1 or 2D, or 2D down to 1D, this also works. Okay. Okay, and so this is a different objective. I'm no longer preserving all the distances. Some of the distances are going to get really greatly distorted. Okay, for instance, if I look at this distance and between these 2 points, they're going to be mapped to these 2 locations. And this particular distance between the 2 green circled points is now getting greatly distorted. I'm no longer trying to preserve all of them, but I'm trying to kind of like my best possible. The best possible in the sense that it's a subspace that I'm trying to minimize the sum of the squares of all these distances that I'm projecting. Okay. But I won't have as strong guarantees for my analysis. Sometimes people say, well, sum of squared, the other reason you might use squared error is it kind of corresponds with normal noise, because the log of a normal looks like a squared error. And so I'm kind of preserving some normal noise. Maybe I'm denoising my data and then working on a subspace that is kind of, I've removed the noise. Probably like wishful thinking, but there's some arguments for that as well. Okay, and so my goal, okay, for this is to find a k-dimensional subspace B. And in fact, I want to find B star, which is going to be arg min over all these subspaces B. Of the sum of squared error from A to B. Okay, so this is now what I want to solve. And it turns out if I set the problem up this way because there's an exact solution. I mean, up to kind of, depending on how much of a linear algebra purist you are, kind of a more or less an exact solution for this and a fairly simple algorithm. Okay, kind of like, if you remember the Lloyd's algorithm for k-means, it worked. There was this really clever algorithm. I kept taking the mean over and over again. This is stronger guarantees than that. This is, again, somewhat of an iterative algorithm under the hood, but you guarantee it converges to the right answer. Okay. Okay. And so the key tool, the key tool will be the singular, I'll write it on the next page, the SVD, the singular value decomposition. And this will pretty much give me this answer. And I say pretty much, not exactly. It will not exactly give me this answer, but I'll have to do a little bit of work first. And this will eventually lead to principal component analysis. Component analysis, also known as PCA, which is what is actually going to solve this problem. Okay, it's going to be a little bit of pre-processing first. We kind of factor out the average and we get PCA, but the SVD is the key tool behind this. Okay, so now I'm going to talk about this singular value decomposition. Okay. And you might see if you've seen my book before, slides may look like the book, but actually the book looks like the slides. Okay, so I'm not copying from the book here. Okay, so okay, so this singular, so there's a number of you who have maybe not seen the singular value decomposition before. It is a way of taking a matrix. Now my data, I'm thinking of it as a matrix. I'm writing it as a rectangle. I like to think of matrices as rectangles, and I'm going to turn it into a decomposition into 3 matrices that are going to be very useful, that are much bigger than the original matrix. Okay, and let's kind of just walk through what properties these have. Even if you have seen before, hopefully good review. This U is going to be an orthogonal matrix. And what it means is that the columns of U, I'll call this UI, these are going to be, UI is going to be a unit vector, and UI dot UI prime is going to be 0. So these are going to be orthogonal to each other, and these columns are going to be unit vectors. Okay, this is going to be this matrix is D by n. So the U matrix needs to be n by n. Okay, so typically we want more data points when we have dimensions. Maybe this isn't always true anymore. But then this matrix is going to be much bigger than A, right? U is much bigger than A. But the good news is that there's another matrix over here, S. These are going to have the singular values in it, which are the points along the axis here. This is going to be SII is going to be, maybe we'll call sigma I. These are going to be some values here, and everything else is going to be 0. So this is all 0. Off the diagonal is 0. So it's mostly zeros except for D things along the diagonal. Okay. What that means is because this part of the matrix below here is 0, right? This whole part down here is 0, that if I look at the n minus D kind of columns here, it does not really matter what these are, because in this, if I multiply these matrices back together again, they're getting multiplied by the bottom part here, so these are going to be multiplied by zeros, so they don't really. Okay, so this is a big matrix, but this part of it doesn't matter. Okay, other than maybe it being orthogonal to this vector and there being unit vectors. Okay, and then the blue matrix, the V transpose, it's written as a transpose, for reasons that will maybe make sense. Now the rows of this, Vj, are going to be, these are called the right singular vectors. And I'm going to have that the rows Vj are going to be equal to 1, and that Vj prime are, the dot with each other are 0, so these are also orthogonal to each other. Okay, so these rows of Vj in the d-dimensional space are going to give me a different d-dimensional basis. So I'm going to get a different set of coordinate axes. Think of the original coordinate, and I'm rotating them by this Vj matrices. I have d new kind of coordinate system, and I can write any point in this coordinate system. In fact, multiplying a point going from a data point in RD and going V transpose X is also going to be in RD, but it's going to be written as a vector in another coordinate system. Okay, and the coordinate system will be the length along each of these the unit vectors, V1 through Vd. Okay, and so see, it's another picture of this thing here. Yep, so what I said before, these are the left singular vectors, the columns of U, the rows of V because it's been transposed. V is orthogonal, but so the transpose means the rows are that give me the basis. Those are the right singular vectors. The singular values are along this kind of the axis here. The other thing we have about the singular values is that sigma 1 is greater or equal to sigma 2 is greater or equal than sigma d, okay? And so one way of thinking about how to represent this matrix in the data is that I can kind of think about taking a unit vector x, okay, and I want to multiply a times a unit vector x, and this will give me a vector as the output here, right? X, to multiply it by it, x would need to be in RD. And so I could look at the norm, the length of this vector in any direction. And for any matrix A, this will define, and it's going to define an ellipse. If I've centered it, so I've removed, so I have it so that the average of all the data points is the origin, it'll be an ellipse around the origin. The right singular vectors are going to define the basis, the axis of these ellipses, where it's stretched along. Okay, and the singular values then tell me how far to stretch this ellipse. Is this all kind of seen something like this before? Maybe, or is this a new way of thinking about it? Okay. Not getting as much excitement from the crowd today. So, well, I know it's a lot of stuff here. Okay, so what we would like to do, and the cool thing about the SVD is it kind of tells you how to do a low rank approximation. Okay, and we can think of this low rank approximation. So we want to do, we want B to be the subspace of a low rank approximation of A, okay? And so I can think about this by kind of writing out a sum over projection onto B squared, okay? And let's look at what this sum means in terms of the basis defined by the right singular vectors. Okay, so I can rewrite this, but I'm going to rewrite A as Vj, actually a sum. I can write this in the basis defined by the right singular vectors. I do this by Vj dot A, okay? So this, if the Vj's are from the basis of the right singular vectors, I have in right here, this is AI. This is equal to AI. I've just written it in the basis of, this is V1, V2, and now I've written AI by the kind of in the basis defined by these rights, so singular vectors. And so I'm gonna use the top k of these singular vectors to write this projection onto bk. Okay, so what I'm gonna instead think about is summing up to k. So instead of going the d terms, I'm going to go to k terms. Vj dot AI. Okay, so I'm going to say my projection here, this is this guy here. But this is only where B is defined by the right singular vectors. So I'm going to say B is going to be equal V1, V2 up to Vk, where these are the the right singular vectors of A. Okay? So I'm going to kind of work out some nice properties about this. So what this means, the fact I use the right singular vectors, and this gives me a nice basis of the data, means I can actually write this as, first I could say, well, a lot of these are two sums over basically the same terms now, and I can just say what terms are left. Now if J equals K plus 1 up to D, so the first K terms, which are going to be the largest terms, I'm going to factor out. And all I have left are these Vj AI squared. Okay, so because there are two sums here and they're summing over, all the elements are the same for the first K terms, I only have the K plus 1 to D terms left. Okay, now I can say, I can use the Pythagorean theorem to factor out, to factor the sum out, sum over I, sum over J equals K plus 1 up to D. Okay, because of the Pythagorean theorem and these Vj terms are independent, I can write the distance between two things. This is now the norm of Aj in the lower part of the basis. I'm writing the sum of the squared terms. I can take this the sum outside of here by the Pythagorean theorem. Okay. Once I've done this is by the Pythagorean theorem. Now I want to observe that this is going to be a unit vector. So that means it does not play a role in the norm here. Okay, so that means I can factor this guy out as well. And then the norm, and then because it's a dot product, the inside is a scalar. Okay, so I get sum over I, sum over J equals K plus 1, just Vj AI squared. Okay, because this dot product is a scalar. This was a unit vector, so it didn't contribute to the norm, so I can throw that away. Okay, and now I can swap the order of the sums up to D. Okay, what does this equal? Looking at this term, this is actually the squared norm along the direction Vj of all the terms in A. Right, so this term is, now I have sum over J equals 1, K plus 1 up to D of A times Vj squared. And this turns out is just going to be the sum K plus 1 to D of the Jth singular value squared. So this term, the amount of norm, the amount of squared norm along the Jth right singular vector is the Jth singular value squared. Okay, so this says if I use the kind of the basis defined by the SVD to define this projection B, then my residual, the sum of the squared residuals is going to be the sum of the squared singular values. Okay. And so if I want to find a k-dimensional subspace in this form, that's just a projection onto a subspace through the origin, then this turns out to be optimal, because what the SVD gives you is the optimal way of doing this. And I can determine what value k I want, and the sum of the squared residuals is the sum of the squared singular values. Okay, so it's kind of the key math that puts this all together, but it turns out the SVD gives you the decomposition which is optimal in this sense. Okay. Okay. little bit of math. I will try not to go through too much more derivations in this lecture. Oh, we're doing really good. Okay. So if we think about this in terms of this picture I drew before, instead of zeroing out before, we talked about kind of taking this region and making this all zeros. When I do a best rank K approximation, I'm putting zeros up to another layer here. I'm saying I'm going to not count the mass from the small singular values here. And I'm turning those into zeros. I'm not counting them in kind of in this projection. That's the part that's getting projected out. Okay, what that effectively doing is it means before this part did not matter, but now I'm extending that up to the terms between, this is K plus 1 up to D, and this was up to N. Before, these things don't matter. Now this part doesn't matter either. And this singular and this right singular vectors after the first K, I'm also effectively throwing away. Okay, so I can reconstruct A this way. If I call A K, what I'm implying here is UK, SK, BK transpose, which I can write this as J equals 1 up to K. This UJ, which is a vector, sigma J, which is the singular value, VK transpose, VJ transpose. Okay, so when I multiply this together, I'm multiplying a vector, a scalar, and a vector again. And I'm claiming I get back a matrix. I'm claiming this is going to be in Rn by D again. How does that make sense by multiplying a vector, a scalar, and a vector again? How do I get some of these get back to N by D? Kind of what went on here.
If U is an N by N matrix, B is a D by D matrix. You multiply them together.
Yeah, okay, so this, okay, great. So U sub K is still, I have these other parts here, but it doesn't matter. This is still an N by N matrix. This is N by D, and this is D by D. D by E transpose still D by D. So then the output is the first N here and the last D here, it's N by D, right? And I claim this is another way of writing it, where I'm summing over the first left singular vector times the singular value times the right singular vector transpose. Okay, how do I get back an N by D matrix using terms that look like this? I have to add things up. So that means each of these terms needs to be N by D. Well, I've multiplied a vector, a scalar, and a vector. Well, I can rewrite this. It would be fine to write a sub k, j equals 1 up to k. I can factor out the sigma j, because this is the only. Okay, so this guy has all the scale information. So that is kind of tells me how important something is. The larger the sigma j is, the larger this is, the more important that component is. That gives me a weight to it. What's happening with uj and vj transpose? What can I multiply those together? Uj is going to be, what's the dimensions of uj? It's a vector, right? Can I think of it as a matrix? A very skinny matrix. If I thought of a vector as a very skinny matrix, an n-dimensional vector, what would its dimensions be? Well, uj is, you're close. Uj is this guy, right? So this is uj. So what's its dimensions? It would be n by 1. All right, it's the rows and the columns. Okay, so it's right. So uj, this guy is n by 1, and then I'm multiplying it by vj. What is vj is in? Remember, it's a row vector now because I'm in v transpose. So I've turned my interesting things, which are columns, into rows, right? So what is the dimension of vj? 1 by d. So now I multiply, or vj, say vj transpose. Transpose is 1 by d. That's this row here. So if I multiply uj, an n by 1 by a 1 by d matrix, well, that works. The ones are allowed. The ones are the ones that need to match, right? So I've done this, and I've output is an n by d matrix from just 2 vectors. This is an outer product, okay? So the entry of the ith j entry, or the rc entry, is the rth kind of element from u multiplied by the cth entry times j, right? So I look at all combinations and the outer product. They're unit vectors, so this is kind of like a unit n by d matrix. It kind of has no scale information. So if I looked at the norm, I can define the Frobenius norm of this term. The Frobenius norm of this term, uj vj transpose Frobenius norm, what is it going to equal? 1. It's always going to equal 1. It's got no scale information in it. It's just kind of, it's got the directional information encoded in vj and vj transpose and uj, but no scale information. All the scale information is in sigma j. Okay, so I've got a rank 1. This is going to be a rank 1 matrix in d dimensions, in n by d dimensions, and then I multiply it by a scale component, and I'm going to add k of these things up, and so it's going to be rank k. And they're all going to effectively be orthogonal to each other. They're all going to add up in some nice way, and this will give me a rank k approximation, right? If I looked at the rank of A is equal to the number of non-zero singular values of it. And I've only added up k terms, and I've zeroed out the singular values. So this is kind of the rank k approximation. And for many ways of defining best, this is the best rank k approximation of the matrix. In terms of, it's got the largest Frobenius norm of a rank k kind of so this, for instance, so if I want to arg, let's say min over all things of rank rank k of A minus B, either a Frobenius norm or a 2 norm, then I can set the answer to this is B is equal to A sub, right? The one that optimizes this. Okay, so this is kind of the best approximation of A in terms of think of these residuals that we talked about before in terms of, but I restrict that the rank is K. When I think of the rank of it being K, what that implies geometrically is that there exists a K-dimensional subspace. It lies in D dimensions, but there's a K-dimensional subspace, and all the data points lie in that K-dimensional subspace. Okay. Okay, and if I went down to 2 dimensions, then those 2 dimensions are where I can draw a picture, right? I can pick the 2 dimensions and draw a picture of this. Okay, so this is, but the thing is the entries in A sub k are still D-dimensional. Every data point has D coordinates to it. How do I get a picture out of this? How do I get this to draw a 2-dimensional picture? Well, I can actually do, so if I want to, if want to draw 2D picture of A in N by D. I've got two ways of doing this. One is, I mean, okay, the answer is step one. Step one is I'm going to compute the SVD of A, and you're not going to do this by hand. You're going to call a highly optimized package for doing it, and this is going to give me USV transpose. Okay, and then option A is I'm going to for all AI, I'm going to represent as AI dot V1, AI dot V2, and this is now a point in 2 dimensions, right? The first coordinate is along the V1 direction. The second coordinate is along V2 direction. Actually, this gives me, yeah. So this is one way of drawing the picture. Yeah. The other way of doing it is I can take U2, right? So this is a 2-dimensional. So if I have AK equals UK SK VK, and let's say UK is going to be equal to U1 U2 up to UK. Well, then I'm going to take these first 2 vectors here. These have n rows in them, right? So these, these have n rows in each of these vectors. Each of those rows corresponds to one of the data points. Okay, so this is option A. This is option B. And these will give the same answer. Okay, so now each data point corresponds with these coordinates here. So I could think of, do I want my projected data point, we'll call it BI, somehow going to be some projection of AI. So I want BI, its first coordinate, I could use U1, the ith coordinate of, right? How should I write this? U1, the ith coordinate, U2, the ith coordinate. But this is not going to give me the right answer. I've omitted the scale information. This does not have the scale information. It tells me kind of in some unscaled version of this. So this is wrong. Okay, so instead I want to do the ith point is going to be sigma 1 U1, the ith coordinate, sigma 2 U2, sigma 2 U2, the ith coordinate, and this will give me a point in 2 dimensions. So these ways are going to be equivalent. This is maybe a more directly reading it off here. The top one is doing another projection. So I'm taking the information at A, the point A, and projecting it, but that information was already pulled out in these other parts of the SVD. Okay, so these are 2 different ways of drawing the picture. Okay. Okay, I want to go back, and I still haven't solved the problem. I told you we almost solved the problem. I want to find the optimal subspace. We'll call this F1, F2, up to Fk, where Fj is going to be in Rd, and Fj will be a unit vector. Where I want F star equals argmin of f of a minus the projection onto f of, or we'll write this as this sum form. Okay, so we want to solve this question. We want to find the optimal subspace that if I project onto that subspace, that I'm going to have as small error as possible. And have we solved this yet? Have we solved this problem with SVD? Who thinks we've solved it? Who thinks we haven't solved it? Okay, and okay. So a few of you know the answer already, but we have not quite solved this question yet, and that's why I wrote more up here yet. The problem is that you can think of having data set that looks like this. Okay, what's going to happen is the SVD will find V1 here and V2 here. And let's say I want to project it onto a one-dimensional subspace. Well, the SVD tells me that we need to project onto this subspace here, because this is the first singular vector. Okay, the first singular vector is going to kind of point in the direction which captures the most spread. And in this case, it's actually V1, not V2 here. What I actually want to do is to find a, I actually want to find a subspace that looks like V1, V2, where it kind of goes through the data. The data lives off this thing that's not going through the origin. The singular value decomposition found you the best decomposition representation of the data, kind of, but forcing that the vectors it's finding the subspace of to be centered around the origin. It's finding these basis vectors with respect to the origin, but the data might not go through the origin. So I'm much better. So I want the subspace to be kind of centered on the data. And I haven't done that yet with the SVD. Okay, so to solve this, we need to apply principal component analysis instead. And there's kind of one step first. You first, step one, I need to center A. So I want to find, we'll call this a bar, which is going to be a 1 bar, a 2 bar, up to a D bar, where a J bar equals 1 over N, I equals 1 up to D of Aij. So I'm basically taking the average of the jth coordinate here. So this first coordinate, I find the average. Okay, I find the average here. This is a 1 bar. And then I find the average in the second coordinate. This is a 2 bar. And then there's a single vector here, a bar, which is an RD, which is the coordinate-wise average. So it's just the mean, which is the mean of all the data. Okay. And then I set a tilde equals the set AI tilde equals AI minus a bar. Okay, so I'm just subtracting the mean off from each of the data points. Okay, and so now I've taken the data points and I've basically recentered it. So I've basically made, you could think of moving all the data points, or you could think of shifting the origin. So it's here. Okay, and then so this is step 1. And then step 2 is I do SVD on 8 on A tilde. And I find the best rank K approximation of A tilde, and this tells me how to do the projection. Okay, there's a lot of literature out there on like the interwebs and so forth that will call something PCA, but actually be doing singular value decomposition and not doing the centering step. This makes a really big difference. It especially makes a big difference if all of your data points happen to be positive. They're very far from the origin. The first singular vector will be just kind of, it's not exactly doing the centering step for you, but it's kind of doing something like the centering step, and it's accounting for that. So if all your data points are positive, or there's a bunch of the data sets are all, one column is all positive, you're going to get some effects like this, and you're going to get a much worse projection, or you're going to have something like all of your singular values are going to be the top ones. They're not going to be spread out evenly over the data set. They're going to be accumulated just based from the centering step. And that's not really finding the directions with the most variation. Okay, so this PCA step is kind of really, really important, where I'm doing the centering. Okay, so this is called centering. Okay, the other reason I think it makes sense is I like to draw an analogy to the variance instead of the kind of the mean. If you think of the SVD, is this first singular vector capturing the direction that has the most variation in it. But it's not the most variance. The variance is the expected squared deviation from the mean. So if I want to look at the expected squared deviation from the mean, which the expected squared norm is sort of capturing, I need to subtract the mean off, right? So the PCA is giving you something like then the first principal component, which was the top right singular vector, is now the direction with the most variance in it. And now this is an accurate thing to say. Okay, but that was not an accurate thing to say with just the SVD, unless you assumed somehow that your data was centered at the. Okay. Okay, great. Very good. We're moving quickly through the good parts of linear algebra. So, okay, one more piece of the puzzle. Okay, how many people remember how the SVD connects to eigendecompositions? Okay, well, that's the last thing we're going to talk about today. And then the next two lectures, we're going to talk about kind of some newer stuff you probably, hopefully have not seen before, or at least maybe seen glimpses of them. Okay, so eigendecomposition. Okay, so an eigendecomposition. What does eigendecomposition take as input? A bunch of you said you've seen eigendecomposition before. What does it take as input? Square matrix, good. So the input now is, I'm going to have a square matrix. So I'm going to call this an R d by d. Okay. And in this class and in most of data analysis, we're going to have the luxury of saying something nice about the square matrix, that it's going to be positive. So definite, or maybe positive semi-definite. Okay, do you remember what those mean? What does it mean for a square matrix to be positive definite? Okay, so I'm going to write one definition up, and then we'll get to a much easier definition of it. Okay, it means for any x in Rd that x m is x transpose m. Okay, so x is in Rd, it's a vector. Okay, it's so X transpose is 1 by D, so I can multiply it by D matrix, which I can multiply by a D by 1 vector. So this is gonna, the result of this is gonna be a scalar, right? So if I, in this way, and this is always greater than 0, and it's PSD if it is greater or equal than 0. So it might be 0 if it's positive semi-definite, but if it's positive definite, it's always greater than 0. Seems like a really amazing property, right? It's always greater than 0. But it's kind of like you're squaring X, so maybe that's not, so squared values are always greater than 0. So maybe that seems reasonable. Maybe not. I don't know. Okay. We cannot worry about this because we're almost always going to get the M matrices we have by having, we're going to say M is going to be equal to A transpose A for some A in N by D. Okay. If we construct our square matrix in this way, it's always going to be positive semi-definite. If D is less than N and A is full rank, then this is going to be positive definite. If it's not full rank, it might be positive semi-definite, and you might get a 0. So if we construct our M matrix this way, which we always basically are in this class and in a lot of the analysis, it's always going to be positive definite or positive semi-definite if A is low rank. It's not full rank. Okay, so we're going to start with a full rank matrix, and it's going to be, and it's in the reals, and there's a lot of stuff you may have learned in linear algebra class about weird stuff that can happen with eigendecompositions. If this is your input, those weird things don't happen. Okay. So now we want to talk about eigendecomposition, but remembering here, and I remember I used A as an N by D matrix. Okay, so what is an eigenvector? An eigenvector V in Rd for M in D by D, that's positive definite. Then I have that M times V is going to be equal to lambda times V. Okay, this this is the eigenvector. In German, eigen means self. So I multiply the matrix by a vector, I get back a scaled version of the vector. Okay, and that scaling, okay, this is a scalar value. This is a scalar. This is it's a real value, and this is an eigen value. It tells you how much it's scaled. Okay, some eigenvectors will get scaled to be much bigger, some will get scaled to get smaller. Okay, eigenvectors, eigenvalues. Okay, for a positive definite matrix, there are going to be D eigenvector value pairs. Okay, so these are going to be V1 lambda 1, V2 lambda 2, Vd lambda d. Okay, and if it's positive semi-definite, what's going to happen is some of the lambdas are going to be 0. Okay, and so that's the only difference. We're going to have that Vj dot Vj prime is going to be equal to 0. Okay, and we set these. We can make a choice. We said it's an eigenvector if Vj is going to be is a unit vector. Okay, so maybe this is starting to look familiar from the SVD. Okay, and so it turns out that these are going to kind of act like this, the singular, right singular vectors in the singular values. Okay, so I can put all these, I can put a matrix V, where this is V1, this is V2, right? And so this will be an R D by D matrix. Okay, this we'll call this matrix V, and I'll put all the lambda values into diagonal matrix, a diagonal matrix here. We'll call this lambda 1, lambda 2, and lambda D, and we'll have the property that M is going to be V, I'll call this matrix L, L, V transpose. This is the eigendecomposition. I've turned the big square matrix into three square matrices. And one of them is going to be a diagonal matrix, so these terms are all zeros. Okay, so this is the eigendecomposition, what the result of it is. Again, I won't talk about algorithms for in this class, but they're black box algorithms. The next lecture will kind of be similar to some algorithms about it. Okay, but at a very, very large scale. Okay, and so how does this relate to this singular value decomposition? Okay, well, let's start now. Let's start with A is in N by D, and A, we're going to do a singular value decomposition. So we're going to get A U V V transpose. And now I'm going to write my M as A transpose A, which is going to be equal to, so if you transpose a matrix, is US transpose. Yeah, so if I have a matrix written as a product, and so A transpose, if I take the product of three matrices and I take the transpose, what I do is I reverse the order and I transpose each of the terms. Okay, and so that's how I got A transpose as the first term here. Okay, now what does this mean? Well, the U if I write this as VS transpose U transpose U S V transpose, well, if I look at this middle term here, these are orthogonal matrices. And so when I multiply them together, I'm just going to get the identity. Each of the individual vectors dots by itself, right? It's orthogonal matrix. Each column is orthogonal to each other. And if I multiply a unit vector by itself, I get 1. And if I work all this out, when I multiply U transpose by U, well, for orthogonal matrices, the transpose is an inverse. And so I'm getting the identity here. So this is equal to V S transpose S V transpose. Okay, and now what is S here? Well, S was, remember, S was this diagonal matrix that was all zeros down here. And so now I'm there's some funny stuff that happened with the U transpose U. It's actually a N by N identity matrix, but I really don't care about this bottom part here. So let's pretend only the top part. See, the bottom part kind of disappears anyways inside the identity. So now I just have this two diagonal matrices, S transpose and S, and a transpose of a diagonal matrix is back to itself again, right? Because I transpose it, but the stuff on the diagonal stays the same. When I multiply two diagonal matrices, I'm just multiplying the terms in the middle, each term by itself. So I'm getting V here. I'm going to get sigma 1 squared, sigma 2 squared, up to sigma D squared V transpose here. Okay, now V is an orthogonal matrix, so its columns are orthogonal, D by D. And V transpose, its rows are orthogonal. These are our right singular vectors. This in the middle is a diagonal matrix with entries in it that are in decreasing order. Well, this is just our matrix L. So the jth eigenvector is the jth singular vector squared. And the right singular vectors are the eigenvectors. Okay, so the right singular vectors are equal to the eigenvectors. Okay, and the eigen values are equal to the squared singular values. Okay, so these are really the same sort of object. They both tell you kind of how to, the best orthogonal decomposition of the data inside the matrix. The eigendecomposition works on these things that come from multiplying a matrix by itself. Any positive definite matrix, I can write as a product of two matrices, A transpose A. Why do I know that? Because I have the eigendecomposition into V, this diagonal matrix V transpose. Well, if I took, and all these things were square terms, so I could take their square root and split them back up into the two parts, right? And I get these two terms left. And these are valid matrices A transpose and A. The U matrix was just a change of basis here. That got canceled out. Okay, so I can always, any positive definite matrix, I can always write this way. I can always think about getting it from this way of the product of two of these nice data matrices. And that's how we will use it. If you use it for kind of regression, and you're solving a regression problem with a matrix inverse, you can solve it through an eigendecomposition. Okay, as well. If you want to invert a matrix, you can go through the eigendecomposition and do 1 over all the eigenvalues, and it basically inverts the matrix. Right? So anything we'll use in most data analysis, we'll think of these eigendecomposition of these positive definite matrices, and then you have all these nice properties. Let me say one more thing about it before you go. I might write A, instead of A transpose A, I might write it as A transpose, okay, where again, A is an R n by D. Now, I'm going to have that M is an R n by N. Okay, I can still write the eigendecomposition of M gets M now is going to be U L U transpose. Now these are the left singular vectors, right? So now it's U instead of V. It's the left singular vectors. I have N of them instead. And these are still the eigen values, and they're still the squared singular values. If the rank is less than n, right? So the rank, let's say D is less than n, so it's rank D. I'm not going to get n eigenvalues. I'm only going to get D eigenvalues. This will be positive, so semi-definite in this way. But the rest of the eigenvalues are 0, and it still basically behaves all the same way. So you have to be careful whether it's A transpose or A transpose A. We'll sometimes see both of them. Okay, great. So this was your hope maybe a refresher course on the cool parts of linear algebra or a crash course in that. And we'll use this in a couple ways over the next couple of lectures.